Okay, so we are back. We have just finished Unit 3, excuse me, and now we're on to Unit 4. We've been focusing on differentiation, which allows us to be able to find the slope of a curve at any point. But now we're going to start focusing on integration. Well, what's integration? Integration is the exact opposite of differentiation. And integration allows us to find the area under a curve. Woo! That's exciting stuff. So before we dive into integration using purely I almost want to say algebraic, but I guess it's calculus methods, computation methods, that's a good word. I'm going to show you how we can approximate the area under a curve. So we can approximate the area under a curve using something called Riemann sums. Oh my sums. Riemann sums. I don't know if it's Riemann or Riemann. I don't know. I didn't invent this. It's one of our mathematicians on the back of the wall somewhere. And to use Riemann sums to calculate the area under a curve, what you can do is break up that area into separate rectangles and then actually approximate that. So the first one we have is called a left-handed Riemann sum. And that's when you start at the left. So you would start at the leftmost point, draw a rectangle. Then here, this is our leftmost point, we draw a rectangle. Here, our leftmost point, we draw a rectangle. Here, our leftmost point, draw a rectangle. I think you're kind of getting the idea here, right? Then we have a right-handed Riemann sum. Right-handed. So from here, we would still, how many did I use here? 1, 2, 3, 4, 5, 6. So I'm still going to have 1, 2, 3, 4, 5, 6 sums. But instead, I'm going to go from the right-handed side and draw my bar over. Okay, so you can see these are not evenly spaced, but they should be. They're not evenly spaced here, but if you were actually calculating a Riemann sum, they should be. You can see in this one, I would say that we probably have an overestimate here, right? If we were estimating the area under this curve. And here I probably have an underestimate. And that's not always going to be the same for every curve, but you can see what's happening. And our last type of Riemann sum is a midpoint. A midpoint Riemann sum. And there, we're going to still have those 6 bars, 1, 2, 3, 4, 5, 6, but this time we're not going to use the left or the right, we're going to use the midpoint. So we would do the midpoint, we come here, midpoint, here, midpoint, here. I don't know, they're kind of tedious to draw, but hopefully you can get the idea. I don't even know if I did that last one correctly, but anyway, so this one is actually probably the most accurate of the 3 that we've had an example here, but it still looks like we might have a little bit of an underestimate there. Maybe an overestimate, I'm not sure. But what we want to talk about really are definite integrals and how we're going to calculate them. So definite integral definition says, let f be continuous on a to b, and f of x is greater than or equal to 0. That's important because we only want to find something above the curve, all right? We don't want to find anything below. It's going to be a nightmare for the moment. For all x in the interval, let a to b be partitioned into n subintervals of equal length. Those are our rectangles, right? Equal length delta x is equal to b minus a over n. So b is going to be this point here, a is going to be this point here, and n is the number of rectangles. So in these examples, I used 6. Then the definite integral of f over a to b is given by area a is equal to the limit as n approaches infinity of k equals 1 to n of da da da, which is equal to the integral of a to b of f of x dx. Okay, don't worry about that right now. Let's just actually do one of these. So we want to find the area a under the graph of f of x equals 1/2 x plus 1 on the interval 0 to 5 with n equals 5 subintervals using left-handed sums. Okay, so I'm actually going to draw this graph on my calculator just so I can see what this looks like and kind of give you a visual. All right, so we've got a graph here, trace. Why did I move it away from here? Trace, 0, 1. Okay, so at 0, we're at 1. At 1, why would I do that? At 2, we're at 2. Okay, you get it. We've got a graph there, right? 2, 3, 4, 5. We're going from 0 to 5, so I might as well. So from 0 to 5, we want to find this area right here using Riemann sums with a left-handed sum. So we're going to first find delta x. So delta x is going to be equal to b, which is 5, minus a, which is 0, over n, which was given to us, which is equal to 5. So 5, which is equal to 5 over 5, which is, of course, equal to 1. Okay, so that means that the interval between each of ours is going to be equal to 1. So the area is going to be equal to 1 times f of 1. Well, I'll just show you the formula here. Our area is going to be equal to b minus a over n times f of x sub naught plus plus f of x sub n. So I don't really love how this is written, but that is what the formula is. Let me check that before I go on. Okay, this is a minor thing, but I actually think that this is supposed to be n minus 1. But anyway, you'll see it as I do an example. So our area here is going to be equal to 1 times f sub naught. Where are we starting at? We're starting from the left, so we're starting at 0. So we're going to have f of 0, right, plus f of, and then we're just moving 1 over, plus f of 1, plus f of 2, plus f of 3, plus f of 4. And actually, you can see we've got 1, 2, 3, 4, 5. We need to have 5 ends, so we've got this. So our area is equal to 1 times, well, 0 is going to be 1, plus 1/2 plus 1 is like 3/2, plus 2 is going to be, 2 plus 1, or 1 plus 1 is 2, plus 3/2 plus 1 is 5/2, plus 2 plus 1 is 3. So this is going to be equal to 1 plus 8/2 is 4, 5, 6, 7, 8, 9, 10. So the area under this curve is equal to 10. Now, if I wanted to do this from the right-hand side, I would just do this exact same work, but instead of starting at 0, I would start from 1. And actually, if I were doing it, I would probably start at 5 and then go backwards, just because I think it's easier to think of it that way. So let's do some of those. We're going to do one problem, and we're going to go through and do a bunch of examples just on the one work. So the table below shows the velocity v of t in feet per second of a car traveling on a straight road over a 50-second time interval. We want to estimate the distance the car traveled over this interval using right-hand sums and left-hand sums, along with 2 different approximation techniques, the midpoint and trapezoid rules. Okay, I haven't taught you trapezoid yet, but I'm going to teach it to you with this example. So, we're asked to estimate the total distance traveled by the car using the left-handed sum method with 5 partitions of equal length. Luckily, we've already done this, so we are familiar with this technique. So, I'm going to draw kind of like a rough graph here, right? So, we've got, let's see here, I'll go up to, looks like t here. T is 50 and v of t is 80, so I'm going to go like 20, 40, 60, 80, okay? And then here t goes up to 50, so I'll just do 10, 20, 30, 40, 50, okay? And if I graph this, I won't make you watch me graph this. Pause. All right, I graphed it off camera. You know how to graph. You've seen me do it before. It's boring. Okay, so we want to find this left-handed sum. Well, first the thing that we need to do is figure out what our delta x over n is going to be. So our b, if we're starting from the left, right, we want to find it over this entire time. B is going to be 50 minus a is 0 over how many partitions are we going to have? 5, right? With 5 partitions. So this is equal to 10. So our area here with the left-hand sum is approximately, or equal to, I guess, equal to 10 times, and we're going to just calculate these areas. So we're going to have f of 0 plus f of 10 plus f of 20 plus f of 30 plus f of 40. 1, 2, 3, 4, 5. Oh goodness, do I have to do this 5 times? 1 second. Yeah, 5. I don't know what I was thinking. Okay, so this is going to be equal to 10 times. Well, f of 0 is just 0, plus 20, plus 52. Oops, I didn't need to put that parentheses there. Plus 80, plus 77, which equals, I'll do it for you fast. I would speed up through this part if I were you. Oops, 229 times 10 is equal to 2,290 feet. Okay, so far so good. So now let's estimate the same information using right-hand sums. So our right-hand sum, we're going to have the exact same delta x over n. So our area with the right-hand sum is going to be equal to 10 times, and this time I'm going to start from the right and go back. Just like I mentioned earlier, I think it's easier to think of it that way. So we're going to have f of 50 plus f of 40 plus f of 30 plus f of 20 plus f of 10. So that's going to be equal 10 times 74 plus 77 plus 80 plus 52 plus 20. Woo! All right. So this is 10 times 303, which equals 3,030 feet. Okay, you can see that these approximations here, which is what I really should be using, those squiggly lines, approximations. Here, we look like we have probably an under approximation, right? If we're going from the left and we were drawing these bars here, and you can do that if you want, you're probably going to have an under approximation. But if we go from the right, it looks like we would probably have an over approximation. Well, let's now actually use the midpoint sum with 5 partitions. So 5 partitions, we're still going from 0 to 50. We're still going to have the same delta x over n. So our area with midpoint sums, I'll call it MPSs, is going to be equal to 10 times, well, now we need to find f of, we're going to have f of 5, right? Because it's a midpoint between 5 and 10. So f of 5 plus f of 15 plus f of 25 plus f of 35 plus f of 45. Whew. All right, we still got 5 terms there. So this is going to be 10 times 14 plus 28. I almost wrote 15. 28 plus 70 plus 86 plus 70. So we have 10 times 268, which equals 2,680. Woohoo! And again, that's in feet. All right, so the last one we want to use is the trapezoidal rule. And this is the one that I haven't talked about yet, but a trapezoidal rule is even more similar than the left hand, right hand. Because left hand, right hand, we were drawing with a rectangle, right? I'll do this in green here. If we're using a trapezoid, what we're going to do with these 5 partitions is we're going to basically connect them from one to the other, right? So if we're there, we go to like 20, we're going to have trapezoids actually, right? We're going to have actual trapezoids that kind of get even closer to the curve. And this is not well drawn, but you can see that this is closer to the curve than, say, like if I just had my rectangles like I was doing earlier, right? So this is closer than like this. Yeah, of course it is. That's a right-hand sum, as you can see. And I'm not going to draw the left because I just don't feel like it. So, trapezoidal rule, we actually have a formula for this. Okay, so the formula for the trapezoidal rule is that our area is going to be equal to delta x over 2, the change of x over 2, times f of x sub naught, that's where we begin, plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus forever plus 2 times f of x sub n minus 1, oops, plus f of x sub n. Okay, so you can see here that what we have here is our delta x over 2 times the first term times 2 times all the in-between terms times the last term. So let's actually find our area for this. So for this one, we are going to have 10 is our delta x, right? Our delta x was that b minus a delta x, I'll just write it over here. Delta x is equal to b minus a over n. So we're going, and that in this situation has been equal to 10 over 2 times. Okay, so we're going from 0 to 50. So we're going to have f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3 plus 1, 2, 3, 4. Yep, okay. 2 times f of 4 plus f of 5. Okay? Right? So this should work out. So if we get this is going to be 5 times, well, 0, it's kind of, I think you're like losing my whole screen here. So hopefully you can kind of take some notes and remember what this table is. But I can't really zoom out anymore because this is extended almost as far as it'll go. So we're going to have, oops, kind of tilted there. All right, we're going to have f of 0 is 0 plus 2 times, and actually what I should be using here is not 1, but the 10, 20, 30, 40, 50, right? So 2 times 20 plus 2 times 52 plus 2 times 80 plus 2 times 77 plus 74. And this is going to be equal to 5 times 40 plus 104 plus 160 plus, well, I guess I should probably know what 77 times 2 is, but I don't. 154 plus 74. And I'm mathing it up. That's adding for you kids. So this is equal to 5 times 532, which equals 2,660 feet. Now, just a quick little trick here. If I take the average of the left and the right hand sum, I'm going to do that real quick. If I take 2,290 plus 3,030 and I divide that by 2, I actually get, so this is going to be equal to 5320 divided by 2, which equals, boom, 2,000. Why did I ruin it like that? It equals 2,660 feet. So the trapezoidal rule is actually the average between the left hand and the right hand sum. And that should be really, really interesting to you, because we saw earlier when we were finding the left hand and the right hand, we knew we had an underestimate, we had an overestimate. So the trapezoidal rule allows us to kind of find the average of that and tighten up the area under the curve. So as we go on in the future, we will have even more accurate ways to calculate this area, and it's just going to get really exciting. I enjoy integration, so I hope that you do as well. This is just the very beginning of it. All right, see you soon in class. If you have questions, leave them in the comments. None of you ever do, but that doesn't matter. I still care about you. Okay, see you later. Bye.